Corey Boone and Caitlin Williams. This is Lab 11 Diffraction. We're Lab Group G.
To measure the diffraction patterns from different apertures, we have a collimated laser source 1 meter away from the aperture, followed by a focusing lens. We then follow by a camera behind a lens of focal length 65 millimeters. The distance from the lens to the focus plane of the camera is 130 millimeters, twice the focal length of the lens. The Fraunhofer region occurs at a Fresnel number less than 0.01. Using this equation, we calculate that this occurs at a distance of 7,740 meters for all the straight fringes. Thankfully, we didn't have to be this far away to observe this region because we used the lens to focus this on the camera. The Fraunhofer region occurs at a Fresnel number of less than 0.01. Using this equation, we calculate that this occurs for all the straight apertures at a distance of 7,740 meters. Thankfully, we didn't have to be this far away to observe this region as we focus it onto the camera using a lens. For each single slit aperture, from left to right, we have an image of the aperture, an image of the Fresnel region, and an image of the Fraunhofer region. The vertical image of the slit in the Fresnel region collapses and becomes horizontal as you move out into the Fraunhofer region. The Fraunhofer image is a Fourier transform of the aperture, and its intensity is described by a sinc function. The Fraunhofer pattern gets smaller with increasing slit width. It has an inverse relationship. For each double slit aperture from left to right, we have an image of the aperture, an image of the Fresnel region, and an image of the Fraunhofer region. As the aperture width increases, the Fraunhofer image compresses. A larger slit separation also makes the Fraunhofer image more compressed. The Fresnel image of a circular aperture is concentric rings. As you zoom in and out, you can see a different Fresnel number of rings. The Fraunhofer image is a bright dot surrounded by vertical and horizontal bright and dark fringes. The Fresnel image from a triangular aperture is fringes expanding from the corners. The Fraunhofer image of a triangular aperture is lines expanding from the corners. The Fresnel image of a square aperture is a bright square with bright and dark fringes expanding from its sides. The Fraunhofer image is a bright dot with fringes coming out of it vertically and horizontally. The Fresnel image of a rectangular aperture is a bright rectangle with fringes expanding from its sides. The Fraunhofer image is an elliptical dot surrounded by vertical and horizontal bright and dark fringes.
In part C of the lab, we take the image of a circular aperture in Fraunhofer region and plot it against a sombrero squared function. Our data is the blue data, and we were able to get a first fringe intensity of 0.01786, which is 3% error. For our second fringe maximum intensity, we got 0.0059, which is 44% error due to the fact that we couldn't image the circular fringe correctly. The distance between the maximum and the first minima are 27 and 25, which is almost symmetrical. In part B, we took the image of a rectangular aperture in Fraunhofer region and retrofitted it to a sinc squared function. The ratio of the first maximum intensity is 0.05, which is 11% error. The ratio of the second maximum intensity is 0.0183, which is 12.5% error. The separation between the maximum and the minima was 24 and 28, which is less symmetrical than the circular function.
To determine the resolution limit of two headlights, it was assumed that a camera has a focal length f and a lens diameter d. The minimum separation between the airy spots of both headlights is 1.22 lambda f over d. Using similar triangles, it was found that the distance at which this resolution limit occurs is d over 0.61 lambda.